Johannsen from Ludwig-Maximilians-Universität, Munich, and he will talk about separation between propositional proof systems and systems related to class learning.
Yes, thank you. So this talk is the latest installment of my ongoing series of results trying to understand the strengths and limitations of certain algorithms used in propositional satisfiability solving. And so we have heard here before that propositional satisfiability solvers are have become very powerful in the last years, say 10, 15 years, and have become very successful also in industrial applications. And so it's a worthwhile program to try to understand what makes them so powerful and where their limitations are. Most of these contemporary solvers are in some way based on branching and backtracking, and therefore their runs naturally correspond to resolution proofs. And so let me start by briefly reminding you of what resolution is. We have seen this in this workshop several times already. So the resolution proof system operates with clauses, which are disjunctions of literals. Literals are variables or negated variables. And we say the width of a clause is just the number of literals in it. And a formula in conjunctive normal form is a conjunction of clauses. And then the resolution proof system is actually a refutation system for certifying unsatisfiability of formulas in conjunctive normal form. And its main ingredient is the resolution rule. So if you have two clauses, which one contains x positively, the other contains x negatively, then the resolvent of these two clauses with respect to x is the union of C without the x and D without the not x. And so a resolution proof then is, first we define a resolution derivation of a clause from a formula is a DAG that's labeled with clauses, which has exactly one thing, which is labeled with the clause that is being derived. And if we have a vertex with two predecessors, then the vertex is labeled with the resolvent of the labels of its predecessors. And every source node is labeled with one clause from the formula. So if this DAG happens to be a tree, then we call the proof tree-like. And a resolution refutation of F is a derivation of the empty clause from F. So it's very well known that this is a sound and complete refutation system. So a formula has a refutation in resolution if and only if it is unsatisfiable. So that's a brief reminder of what the resolution proof system is. The resolution proof system is very much related to this basic ingredient of set-solving algorithms, the classic DLL algorithm, named after the authors Davis, Lodeman, and Loveland, who introduced this in 1962. So this is a basic backtracking procedure. The algorithm is called for a formula F and partial assignment alpha, which is empty in the outermost call. And first you test if the formula is already satisfied by alpha, then you return alpha. Or if one of the clauses in F is already empty under alpha, then you return it's unsatisfiable. And otherwise you pick one variable which has not been set yet and recursively solve the two cases where alpha is extended by setting x to 0 and by setting x to 1. So this is a very basic recursive backtracking procedure, which I call the DLL algorithm. And which is what is well known, the classical result is that if an unsatisfiable formula can be refuted by this algorithm in S steps, then it has a tree-like resolution refutation of size S. And in fact, this is very easy to see. If you run this algorithm on an unsatisfiable formula, then it spans a search tree, and this search tree is actually a resolution refutation of the formula. and also the converse holds. If you have a resolution refutation of size S, then you can use this as a blueprint to obtain a DLL run which solves it in time in S steps by choosing the variable that is resolved on at each node. So this is the tight back and forth correspondence between the runs of the DLL algorithm and resolution refutations of the formula. So the contemporary set solvers use several extensions and modifications of this very basic algorithms, and so one of the most successful of these extensions is clause learning, which is the major topic I'm going to talk about. So let me briefly give you a very high-level view of how clause learning works. So in the case when the algorithm runs into a conflict, that is, one of the clauses in the formula is empty under the current partial assignment, then this conflict is analyzed, which means that one computes in some way a sub-assignment of the current assignment, which already suffices to imply this conflict. And then we add a clause to the formula, which is the minimal clause that is falsified by this sub-assignment. And this then allows in later branches of the search to prune the search tree, because if you later and come to another situation where we have some partial assignment extending this alpha prime, then this added clause will become false under this assignment, and there's a conflict immediately, whereas otherwise we would have to do some more reasoning before this conflict occurs. So if we do this every time at every conflict, then our memory will soon be full of learned clauses. So it's not a good idea to learn everything we can learn. So what we need is a good heuristic to decide which clauses to learn and which not to learn. And so in early times, many heuristics were such that they put a bound on the width of clauses to be learned. This turns out not to be too good an idea. So we show here, and we have shown in previous works, that if you learn only short clauses, then this doesn't help very much. So this is something that we have shown before and which we will refine now. In order to do this, we want to use, again, the proof complexity paradigm. And so what we need is a proof system which corresponds to a DLL with clause learning in the same way that the tree resolution corresponds to the plain DLL algorithm. And such a proof system has been defined, in fact, several of those, and one of them was is this one, which I call resolution trees with lemmas, or short RTL. So a resolution tree with lemmas for a formula F is an ordered binary tree, so we need to be able to distinguish left and right children of a node with the following properties. So the root is labeled with the empty clause. If a node has children u and u prime, then it's labeled with the resolvent of the labels of u and u prime. And if v is a leaf, then it's labeled with a clause from the formula. So far so good, we've all seen this before. Now comes the new part. Or it is labeled by a clause which is the label of some node which occurs earlier in the tree. And earlier in the tree means it occurs earlier in the post order of the tree. And if that is the case, then we call such a clause at a leaf a lemma used in the proof. So if you look at this closely, then this is more or less nothing but a fancy way to write DAG-like resolution proofs. But it becomes interesting if you put further restrictions on this class of proofs. For instance, if you insist that they are regular, which means that on every path no variable is resolved twice, or things like this. So then there is the following result in a paper by Sam Buss and Jan Hoffmann and myself, that if an unsatisfiable formula is refuted by a DLL algorithm with clause learning in S steps, then it has an RTL refutation of size polynomially related to S. And moreover, if you look at this proof, then the lemmas used in the proof are among the clauses that are learned by the algorithm. So in fact, this paper by Sam and Jan and myself contains a whole family of systems, and for some of them we have the exact correspondence to DLL with clause learning in the same way that tree resolution exactly corresponds to plain DLL. And so what we want here to do now is we want to show that learning short clauses is bad. So we look at a subsystem of the systems where we restrict the width of the lemmas used. So RTL-K is the subsystem of RTL where every lemma used in a proof is of width at most k. And for this subsystem RTL-K, we proved lower bounds. The width of a clause is just the number of literals. You can also say short clauses. Learning short clauses doesn't help. So so we have already in several earlier works proven lower bounds for this. Let me quickly show you a review of what we have had so far. So the first lower bound that I had for this was already in this paper where we introduced these proof systems, and this is for the proof complexities favorite family of formulas, the pigeonhole principle. So we've shown that the pigeonhole principle formulas require RTL proofs of size 2 to the omega n log n if you restrict the width of lemmas to be n over 2. So if you only use lemmas of width n over 2, then you require this size of proof. So that means if a DLL algorithm with clause learning learns only clauses of width n by 2, then it takes this amount of time roughly. And on the other hand, there is an upper bound for regular resolution for pigeonhole clauses of roughly 2 to the n. So this gives a super polynomial gap between learning only short clauses of length n by 2 and learning arbitrary clauses.
Yeah, so if you don't put any bounds on RTL, this is just resolution.
Yes. Yes. So this shows in principle a super polynomial gap, but of course these formulas are well known to be hard even for full resolution. So we were trying to find a better example, and another better example is in 2009 I found this formula, the ordering principle formulas, which have also appeared in this workshop already. It's a formula saying that in a finite linear ordering always there is a minimal element. So, and these require exponential size to refute if you only use lemmas of length n over 4. So again, this means that when you solve these formulas by learning only for clauses of length n by 4, then you take exponential time, whereas there are regular resolution refutations of polynomial size for these formula. So they can be solved in polynomial time when you learn arbitrary clauses. And in both cases, the lower bound obtained here is of the same asymptotic order of magnitude as the known lower bounds for tree resolution. So in these cases, learning short clauses is no better than no learning at all. So the latter one result was then generalized by, together with Elie Ben-Sasson. We were able to show that every formula which requires large resolution width is hard to refute if you learn only short clauses. So if you require resolution width, so that means every resolution proof requires a formula of width W in it, then every RTL-K refutation is of this exponential size in the width. So this generalizes this. So this is what was known so far, and here comes the new result. So what I'm going to do now is I'm separating the levels. So I'm showing an exponential gap between RTL-K and RTL-K plus 1. So that means for every k, there are a family of formulas fnk, such that the formulas f and k have RTL k plus 1 refutations of polynomial size. So when you learn have lemmas of width k plus 1, then you can prove them efficiently, whereas if you have only lemmas of width k, then you require exponential size to refute these formulas. So what are these formulas? People familiar with proof complexity can more or less guess what they are by this lower bound. So they are come from pebbling formulas. If you see an n over log n, it always hints to pebbling. So what is graph pebbling? So you have a pointed DAG, that is a DAG with exactly one sink, and every node has in degree 2. And then you can play a pebble game on this, where you put pebbles on the vertices. So you can put a pebble on any source, and if a vertex has both its predecessors or all its predecessors pebbles, then you can put a pebble on it, and you can remove pebbles at any time, and this way you continue to put the pebbles on the graph until a pebble is put on the sink. And so the pebbling number of a graph is the minimal number of pebbles you need to reach the sink in this game. And a well-known classic result of Celoni, Paul, and Tarjan from the 70s says that there are families of graphs which have this almost linear pebbling number. It require n by log n many pebbles to reach the sink. So these have n nodes. Graphs of n, size n, which require almost linearly many pebbles to finish this game. So these formula, from these pebbling principle, you can build a formula. So it's a very, first of all, a very simple formula, the implication graph formula for the graph. It's just if you have such a graph, then you have the axiom saying you can put a pebble on a source. Then the axiom saying if you have a pebble on u and u prime, then you can put a pebble on v, and then there's in order to make it contradictory, you say that you cannot put a pebble on the sink. This is a very easy formula. If you look at it, then you see that it's a horned formula. So these formulas are very easy to refute in every kind of proof system. So in order to make them hard, Eli Ben-Sasson and Avi Victorson, Russell and Pagliazzo changed this formula by replacing every variable by the disjunction of two variables, and these formulas imp2 of GE require for a graph, if you refute these in tree resolution, you need an exponential size in the number of pebbles you need in the pebble game. So this is similar to the formulas we use here, but we need a different way to make the pebbling formulas harder, and not just using these or there. So a different way to make a formula harder is XORification. So what is XORification? In XORification, you don't replace a variable by the OR of two variables, but here you replace every variable by the XOR of k variables. So the XORification of a variable is just the XOR of k copies of the variable. The XORification of a negated variable is the negation of that. And then the XORification of a clause is the disjunction of the XORifications of the literals in it expanded into C and F. And then the XORification of a formula is the conjunction of the XORifications of its clauses. So, if we have these implication graph formulas, then we write this thing for its k-fold XORification. So then it's not quite hard to show. You can, by some inductive argument, easily show that if you are allowed to learn lemmas of width k, then you can refute these in linear size, so size which is exponential in the in k, but linear in n. It's exponential in k because already the formula itself is of size exponential in k. So this is the upper bound that we need, and now I'm going to show you the lower bound. So if you have less than k width of clauses to be learned, then you require exponential size to refute these formulas. And if you have seen my previous talks about the results that I mentioned before, then you have already seen the basic blueprint of the proof that will follow. And in fact, this is the easiest instance of this blueprint of proof, and should have been the first one that I have obtained if I had earlier thought of this class of formulas to use as an example there. So how does this lower bound proof work? So now we take the k plus 1-fold XORification of the implication graph formulas and assume that we have a refutation where we only use lemmas of width k, and we want to prove a lower bound for that. So we have this refutation, and then we locate in the proof the first clause, which is short enough, namely of width at most k, so that it can potentially be used as a lemma. And then we look at the subtree below this clause. And then this subtree below this clause is just a tree-like derivation of this clause C from our formula. And what we do then is we find a restriction which makes this formula false, and put this restriction on the whole proof, and then we have a refutation of the restricted formula. So then the restricted proof is a refutation of this formula under this restriction. So in order to be able to say something meaningful about this, we need to make sense of this restricted formula so that we can argue about it. So, and in order to make sense of this formula, we generalize the notion of XORification a little bit. So we introduce a generalized operation of XORification. This generalization has 2 degrees of freedom. So for every variable, we associate 2 bits which control these 2 bits of freedom. So 1 bit of freedom is we can replace some variables not by the XOR of k copies of the variable, but also by the negation of the XOR of 2 variables of these k variables. This is 1 bit, and the other bit is that some variables are not replaced by an XOR of k variables, but remain intact. So this is the other bit. So for a variable, we have 2 bits. The first bit says whether it's replaced by an XOR or not, and the second variable bit says whether it's negated or not. So formally, this is if the first bit is 0, then we replace the variable by the XOR plus the second bit, which is x plus 1 is equal to not x. So the one property of XOR. And if the first bit is 1, then we just replace the variable by 1 copy of the variable plus the second bit. And then we continue as before by for a negative variable, we negate the whole thing, and for a clause, we take the disjunction of the things we replace the literals with and expand it into C and F, and the whole formula is then these translations of the clauses to get taken together. So this is the generalized XORification, and then this helps to make sense of the so we use this notation for it. We put this beta into the lower index. So this can then is a description of what happens if we put such a restriction on the implication graph formula. Namely, if we put a restriction here, this row that we need onto the formula k plus 1 XORified, then we get a generalized 2-fold XORified formula. And how is that? So if you picture the variables in the Pebbling formula, in the XORified Pebbling formula as a rectangular grid, where you have a column for every vertex and a row for every index from 1 to k, then you restrict at most k of these variables, because a restriction that falsifies a clause of width k has sets at most k variables. So you put a restriction of k variables on there. So there are two cases. Either there are two rows, two columns in which variables are restricted. Then that means that in every column there are at least two rows which have not been set. So then you take for these rows, you take for every column two of the variables that have not been set, and everything else is set to 0. But then you have in those rows you have some of the values that had been set, so some of them will have an even number or an odd number of ones, and the rest zeros. So that you have in the remaining formula you have an XOR of two variables, and sometimes negated, sometimes not, because sometimes you have an even or odd number of ones in the columns. And this is one case. The other case is that all the k variables set are in the same column. We have k plus 1 here. If they are all in the same column, then you have this one column where all the variables have been set except for one. And then you just take, in all the other columns, you take two arbitrary variables and set the rest to 0. And in that column, you have just one variable remaining. And that's why you need this other case where some variables, in this case just one variable, is not set, is not replaced by an XOR, but all the other variables are replaced by an XOR of two variables. So this is why the result here can be seen as the twofold generalized XORification of the implication graph formula. So then what we need is a lower bound for that, and for that we can adapt the lower bound for the orified, so to say, implication graph formula by Ben-Sasson and others, and prove the following: that if a tree resolution refutation is given of these generalized XORified formula, then this is of size 2 to the pebbling number of the graph minus a, where a is the number of variables which have not been replaced by an XOR here. So this is a slight generalization of the lower bound by Ben-Sasson, Impagliazzo, and Wigderson. Alistair Urquhart wrote in a recent paper that to adapt the proof of Ben-Sasson and others to the case of XOR, replacing the variables by XOR instead of OR, can be done by literally copying the proof line by line, which I found is not quite true. Even if you don't have this generalization by beta, the modification you need to do is a little subtle, and gets more subtle if you have also, in addition, this generalization. So this gives us our lower bound that we want, because as we have seen in this case that we get in our proof, we have at most one variable which has not been replaced by an XOR. The others are at most, all other variables are replaced by an XOR. It's only one variable where the first bit is 1 and which has not replaced by an XOR. So therefore this subtree is of size exponential in the pebbling number, and therefore the whole proof is of size exponential in the pebbling number. And so this shows our main theorem, that these formulas, the k plus 1-fold XORified implication graph formulas for these graphs of Celoni, Paul, Tarjan, which have almost linear pebbling number, have polynomial size refutations if you have lemmas of width k plus 1, but need exponential size refutations if you only have lemmas of width k. So this gives a separation between these levels of the hierarchy where you allow learning using lemmas of width k plus 1 versus width k. Unfortunately, this does not immediately yield that in a clause learning algorithm, learning clause of one literal more gives an exponential speed up, because if you look back at this, what I said before, So there is this restricted system for which we also have the converse, that from the run of the from the proof we can obtain a run of the algorithm, but there are several restrictions that have to be met by the proof in order for this reverse to hold, and unfortunately one of those restrictions is not true, does not hold for the proofs I produce for the upper bound. So there's still room for some improvement to get the actual separation between in a DLL algorithm learning with k clauses versus learning with k plus 1 clauses. Thank you.
So we can still have a few questions.
But I don't think there's any of this algorithm that tries to select only I mean, it's not, the heuristics are not biased or selecting necessarily small clauses, right? I mean, they're looking for cuts in the graphs. I mean,
I'm not sure. So what people tell me is that in very early times of clause learning, in the first versions of GRASP, they had something like that. And so one of the reasons that it became much more successful with Chaff is because Chaff had this very efficient data structure for unit propagation, which allowed them to store very long clauses and treat very long learned clauses, which could not be handled by previous mechanisms. But I don't know enough about the practical side to really say whether it's true or not.
So is it known at least that if there are exponentially better on some examples than if you don't use close learning? I don't know how to formalize it, but so you are the last question you asked was to show that if you learn larger classes, then you get exponential speed up. But is there any basic result showing that close learning really helps?
Yeah, so there, any example separating tree-like from regular resolution would be an example of formulas which can be solved quickly with clause learning, but need a long time without any clause learning.
Refuted, but these are examples where these algorithms do not find a solution, but are there examples where they find a solution?
in practice, this close learning has been nothing short of revolutionary.
Yes. Yes. So the question is there any formal theorem proving this?
My understanding is that there is actually no such formal method. So there is always in the air. People believe it. I also tend to believe it. Yes. However, a really good argument is missing in the literature. This would be really good to have.
And you have to distinguish the satisfiable case work from the unsatisfiable cases.
Right. That's the question.
Yeah.
So you're talking about the unsatisfiable cases?
No,
The satisfiable cases. Okay.
but even for unsatisfiable cases, is there such a proof?
Well, for unsatisfiable, it's young.
There is a
But
separation.
satisfiable, but if you just guessed the right satisfying assignment, you don't have to do any learning.
No, but
Yes, but you have to formalize it so that it makes sense. If you just guess.
Well, it's a non-deterministic search procedure. Right?
No, but there is a way to do it. I mean, you take, for example, the formula and you choose some variables, let's say, at random, and typically what you get when you assign them is now an unsatisfiable formula.
Right.
So that's why even in a solver case, they spend most of the time. You're trying to solve an unsatisfiable sub-instances of the instance you're given.
Yeah.
Okay, so let's continue the discussion with coffee, and we will reconvene at 11.